This is a video of the workshop ANOVAs in SPSS, and we're going to cover all these different types of ANOVA. You can use the bookmarks to jump to any type you're interested in, but do be aware that they build on each other, so you might want to start with looking at one-way ANOVA. At the end of the workshop, we're going to talk about alpha levels, type 1 and type 2 errors, and what we mean when we talk about the power of a test. This workshop is based on the most common queries we get in the Math Skills Centre, so it might be that your specific problem needs a bit more research. And just to make you aware, all the data that we use in this session is fake, so don't take any conclusions from the results. So the first thing to notice is that ANOVA stands for analysis of variance. So when you're looking for advice, so if you're Googling for information, and that things that say analysis of variance are relevant too. We're going to run these ANOVAs in SPSS, but we don't just want you to understand how to run them, what menus to go to, but to understand what the test is doing and what the output means as well. So let's start with one-way ANOVA. We need some data to play with, so I want you to go back to the Math Skills Centre VLE where you'll have found this video, and there's a file there called workshop data, stride one-way ANOVA. You can do this at the same time, or you can just watch me do it, it's up to you. So once you've opened that, hopefully you'll notice that this is an experiment where we're testing the effect of surface, so whether people run on grass, tarmac or track, on their stride length. So we're measuring people's stride lengths in centimetres. So if you look at the data, you can see each row is a person. So all these people ran on surface 1, all these people ran on surface 2, and different people ran on surface 3, and then these are their stride measurements. If we want to know what 1, 2 and 3 mean, we can go into the variable view and we can see that 1's grass, 2's tarmac and 3's track. In SPSS, we're going to check assumptions. If you're not comfortable with the idea of assumptions, especially in testing for normality, I'd recommend this resource here, which is a journal article, but it's titled A Guide for Non-Statisticians. So I think it's the clearest piece of literature I can find talking about what normal distribution is. We're going to run a one-way ANOVA, and we're going to also at the same time run something called a post hoc test, and the type of post hoc test I'm going to use is Tukey, just because it's quite a common one people use, and then we're going to look at the output. So I'll do that in SPSS, and then I'll come back and recap some key points that I want you to take notice of. So if we're running tests in SPSS, that's kind of the easy bit, to know what menus to go to. There's a lot of good guides out there. What I would probably do is use, if I'm on the internet, I would probably use a guide called Laird, and I would type in the name of the test that I want to do in SPSS. And you should get a guide that looks a bit like this for whatever test you're doing. And it explains the test, and then it talks about the assumptions, and then it gives you very, very clear screenshots of what buttons to press in SPSS, what menus to go to. If we just look at the assumptions, you'll notice that number 1, it talks about your dependent variable being interval or ratio or continuous. This means that in SPSS you would have it coded up as scale. There's another assumption 4, which is talking about outliers. We can check for outliers using box plots. And then assumption 5 talks about checking for normal distribution. So we're going to do that as well. And then assumption 6 talks about another assumption called homogeneity of variances. This is the same as equal variances. So talking about the spread of your data. So using this guide, you could run a one-way ANOVA. So first of all, we're going to demonstrate checking normality. So to do that, we go to Analyze Descriptive Statistics and Explore. We put our dependent variable under dependent list, and then the grouping variable or the independent variable under the factor list. And then clicking on plots, we get an option called histogram, which is going to make us a nice graph. And then we get this normality plots with tests. It's that you're ticking in order to get a Shapiro-Wilk result. So the results come up in the output window. You can see we've got some summary statistics here. What we're interested in, because we're testing for normality, is this box here. So you've got 2 different tests. It's almost personal preference what one you take notice of. I'm going to talk about Shapiro-Wilk, which is quite a common test. And you can see here, this is your p-value under the sig column. And if that's greater than 0.05, then it suggests that we've probably got normally distributed data. Remember I've made up this data, so that's probably why my p-values are so high. And I don't just want to look at the test result, I want to also look at these histograms. So here you can see that's roughly a bell-shaped curve, so normally distributed. This one looks less convincing, but remember that you might want to change the settings of the graph. So what I mean by that, if you click on this graph to open up the chart editor, and then click on the bars, you get this option which is called binning. If you click custom, and you specify here how many bars you want, so I'm going to put it to 5, let's say, and apply that, you can see that now that looks more like a normal distribution. So sometimes it's just the binning that SPSS has chosen to use that will sort of hide that normal distribution. This one's, again, you can see it's not perfect, but I would be fairly happy with that as normal distribution. And then the only other thing that I'm going to check is the QQ plots. So these are your observed data, your actual data, against what we would expect if we had a normal distribution. And then you can see how close to the line that these points are. Again, that's not bad, so I'm going to go with that. You can see there's a couple of points here and here that are probably outliers, but they're not awful. If we wanted to check some outliers, we can go to our box plots. Sometimes outliers are displayed as stars or circles up above or below these box plots, but this data is looking quite good. So now we can actually run the one-way ANOVA. To do that, we'll go to Analyze, Compare Means, and we've got one-way ANOVA at the bottom here. So again, I'm going to put my dependent variable under dependent list, and the grouping variable or the independent variable goes under factor. And then I've got a few options. If I find that there's a significant difference in this test, I won't know where that difference lies between which of the independent levels. So I'm going to do a post hoc test. I click on the post hoc option, and I want to do a Tukey post hoc test. There's lots of different options here. I would say Tukey is quite a popular one. And then under the options button, I quite like to get some descriptives because that will give me the means, which means I can then understand the direction of a test, i.e. which group's higher or lower. So I can tick that. And the other thing I want to tick is this test, homogeneity of variance test. That's going to run me a test of equal variances to make sure that the spread of my data is roughly equal. Click continue and OK. And the first thing I'm going to do in my output is finish checking the assumptions. So I'm going to do that by looking at this box here. This is the homogeneity of variances result. I'm going to use the based on the mean data because I think my data is normally distributed, so the mean's quite a good representation. And my p-value is under here, so that's saying it's above 0.05. There's no differences in the variances of my data, so it's roughly equal, so it's homogeneous. Once I'm happy that my assumptions are met, I can then look at the results of the one-way ANOVA itself, so that's this box here. And I'm going to look at my p-value first on the sig, so I can see that there is a significant difference somewhere in between these three levels of my independence, so between grass, track and tarmac. And I'm also going to report this test statistic here, the F value, so I'd write that in my report. And I'd also write these two types of degrees of freedom. So I've got a degrees of freedom 2 here, and then I've got an error degrees of freedom here. So those 4 pieces of information, that 2, that 3, that 28.198, and this p-value all go into my report. But I'm not finished because I've got a significant effect. I want to see where that difference is. Oh, sorry, I should say. This sum of squares, if you wonder what it is, it's numbers that are calculated during the maths when you calculate one-way ANOVA. If you really want to understand how one-way ANOVA is performed, there's some really good videos online. If you type in ANOVA by hand and watch someone do it by hand, that gives you a good idea of what sum of squares are. So I've got this significant p-value. I want to know what groups, so grass, tarmac, track, which of these there's a significant difference between. So here, this is my post hoc test results. This is my Tukey post hoc test here. So you can see here that the difference, is there a significant difference between grass and tarmac? Yes, there is, because the p-value is significant. Is there a difference between grass and track? Yes, there's a significant difference here. And then it repeats tarmac and grass, but then it compares tarmac and track, and you can see no, there's not a significant difference between tarmac and track. It also gives you an alternative way to think of those results, which is grouping the levels of the independent variable. That might be useful if you've got a lot of levels, if you had 10 levels or something. So it's saying that tarmac and track are in the same group. There's no difference between tarmac and track. But there is a difference between grass and track and grass and tarmac. So it's grouped them in a separate group. So that's one-way ANOVA. Just to reiterate some points, post hoc testing. If that p-value that you get from the ANOVA is not significant, then don't look at that post hoc test, and certainly don't report the post hoc test, because it will just say that there's no differences among your independent levels. And when you're reporting one-way ANOVA, I think the best advice I can give you is to look at journal articles in your discipline to find out the accepted way to report those tests. And also, if your department is asks you to adhere to a certain style of referencing, such as APA, then you want to look at how APA reports a one-way ANOVA. Let's move on to two-way ANOVA now. The 2 in a two-way ANOVA refers to the fact that you've got 2 independent variables now. So before we only had one, which was the type of surface that people were running on. Now we're going to add another one. Just be aware that there's alternative names for this test, so two-way between subjects ANOVA, or some people call it a factorial ANOVA. So if you find advice on those tests, you can take that advice if you're running a two-way ANOVA. So again, going back to the VLE, open up another set of data, but this time it's workshop data stride. We're still looking at a similar experiment, but it's two-way ANOVA. So this is where we've got our independent variable, which is our surface, so just as before. But now we've added another independent, which is the gender of the people that are doing the running. Let's open that up. So same data as before. This is your dependent variable here, a measurement of the person's stride. This is the surface that they're running on, but this is the gender. So we've got some people are given the code 1, some people are given the code 2. And we can see in our variable view what those codes mean. 1 means female and 2 means male. In SPSS, we're going to again check for normality of our data. But when it comes to two-way ANOVA, we've got to do something extra. We've got to split our file, and we'll show you that. Then we're going to run a two-way ANOVA, and we're going to ask SPSS to build us an interaction plot, and we'll talk about what interactions are. And we're also going to do a post hoc test like we did in the one-way ANOVA. And then we'll look at the output. So back into SPSS. And I should say, when you want to know what menus to go to, again, we can look at layered. So if we type into layered two-way ANOVA. Oh, made a spell mistake there. So if we type into Google layered two-way ANOVA, we'll get up a guide, and it's the same format. We've got an explanation of the test, and then we've got some assumptions. So you can see here that assumptions are quite similar to one-way ANOVA. When we get down to assumption 5, this is about normal distribution, but this time it's saying that we've got to check the normal distribution for each combination of the groups. So what that means is we're going to check for 6 groups in our cases. So we're going to take one group female grass, then female tarmac, female track, then male grass, male tarmac, male track. So that's our 6 groups that we have to compare for normal distribution. And similarly, we're going to test for equal variance, but again for each combination of those 2 independent variables. So to do that, we're going to split our file so that a normality test is done in each of those 6 groups. What I'm going to do though is show you what happens if I don't split my file. So if I was going to make the mistake of not splitting my data, I would check normal distribution by going to Analyze, Descriptive Statistics, and Explore. I would put my dependent variable in here, and then I would just put my independents into the factor list. Click on Plots, get a nice histogram, and a Shapiro-Wilk test by ticking that. And then what you'll see is you have a whole load of results which tests it split up 3 ways, grass, tarmac, track. And so we've got 3 results there. and then 3 histograms, which are for grass, tarmac, track, QQ plots. And then what it does is it splits it by gender. So it takes the same data and splits it by gender. And so we get 2 p-values here for male and female. And that's not actually taking the combination of the 2 independent variables. That's not us checking for normality in it for a two-way ANOVA. So let's do that correctly and split the file. We go to Data and Split File. And just now it says Analyze all cases, do not create groups. We want to compare groups. So we want to compare males with females, let's say. We could choose any of our independents to do this. We're going to split our file by gender, click OK, and nothing happens apart from this tiny little line in your output which says split file layered by gender. So you won't actually see anything in your data. It doesn't look different, and that's a bit dangerous because it means you forget that you've got that split file on. Now if I repeat that checking for normality, I go to Analyze Descriptive Statistics and Explore. I'm going to take gender out of there and just put my other independent in here. I'll check that I've ticked the histogram and my normality plots for tests for Shapiro-Wilk. And now you'll see that it split the data differently. So now it's split it into 6 groups. And if we go down to our Shapiro-Wilk tests, we can see that we've got those results for female grass, female tarmac, female track, male grass, male tarmac, male track. And we can look down there and see that they're all normally distributed because I made up the data. Again, we might want to rearrange the bin in there to just check that it is actually normally distributed. And we can have a look at our QQ plots as well. Now what we've got to do is remember to take that split file off. I'm going to demonstrate to you what happens if we don't do that. So if we now go ahead and run our two-way ANOVA without taking that split file off, we'll go to Analyze. General two-way ANOVA is under General Linear Model in univariate. We would put our dependent variable here and then put our independence under fixed factors. I'll not do any of the options this time just because I'm demonstrating what happens when you don't take the split file off. And it's done one test on the female data and then another separate test on the male data. We don't want that. We want it to run one two-way ANOVA. So let's correct that mistake. Go to Data, Split File, and I'm going to click Analyze all cases, do not create groups. Again, nothing really happens except for this little message here which says split file off. Your actual data doesn't look any different. So let's try that again. Let's use this recall button. We'll go to univariate. So this is us running our two-way ANOVA. So we've put our dependent here and our two independents here. Now I'm going to do some options. So again, I want to do a post hoc test because if I have a significant p-value, I want to know where those differences are. Now there's no need to do this for gender because if I get a significant p-value for gender, I know that there's a difference between males and females because I've only got 2 levels for that independent variable. Whereas for the surface, if I get a significant p-value, I won't know where the differences lie. So I'm going to click on post hoc. I'm going to say that I want to run a post hoc for surface, and I'm going to tick Chuki again because that's a type of post hoc test that I want to run. I'm also going to click on options. And again, there's an option here for descriptive statistics. That's just good because I want to know directions. And then there's also a tick box for homogeneity test. So that's going to run a homogeneity of variances test. So a Levene's test for me. And the other thing I want is an interaction plot. To get that, click on plots, and then you've got to say which independent variable you want on the x-axis, and then what one you want to see as separate lines. So it doesn't really matter which you do. I'm going to put surface on the horizontal axis, and then I want two different lines, one for females and one for males. You've got to click add to get that plot there. And I've chosen to do it as a line chart, but some people prefer bar charts. Run that two-way ANOVA. I'm going to start by finishing off checking my assumptions. So we've already checked for normality. This box here checks for homogeneity of variances, so equal variances, and it's run a Levene's test. So I'm going to use this top line here based on the mean, and I can see that my p-value is above 0.05. So I'm happy that there's roughly equal variances. The main result for the two-way ANOVA, is under here. So this tests of between subjects effects, this box here. And what we're going to have is a p-value for our surface independent variable, a p-value for our gender independent variable. So we can see that those are significant. So there is an effect of surface and there is an effect of gender. And then we have an interaction. So here it's saying that those two independent variables work together to have an effect on the dependent variable stride. So gender and surface sort of interact to determine the outcome on the stride. That can be a bit difficult to get your head around, so we're going to talk a bit about interactions. The other thing I'm going to look at is the post hoc test. So that's under this multiple comparisons box again, and it's the same as in the one-way ANOVA. We've got our significant p-values here, and we can tell where the differences lie. Because I've got a significant interaction, I'm going to look at this plot. I might not want to look at this interaction plot if my p-value is not significant for that interaction. The general rule here is if the lines are not parallel, there's no interaction. So here you can see the slope of this line here is more extreme than the slope here. So it's effectively saying that males are, let's say, more affected when they're running on grass compared to the other two, whereas it doesn't make as big a difference to females if they run on grass, but it does still make a difference. So we'll talk a bit more about interactions on the slides. Let's go back to the slides. So you can think of interactions as the dependent reacting to one independent in a different way when you consider the other independent. We could have got any of the plots below, so any of the interactions below. But the thing to notice here is that the first three plots, the lines are not parallel, so we do have an interaction. Whereas here, this last example, they're parallel, so there's no interaction. So in this first plot here, we have males and females, and they're on two different diets. And you can see when we look at weight loss, the dependent, there's an interaction going on with gender and diet, i.e. males and females react differently to these two diets. The second graph is about car size and whether we've got a standard or a new filter. And again, medium cars are reacting quite differently in terms of the dependent noise, dependent on whether that's a new or a standard filter. And then here we've got two bacterial strains, and we're looking at their growth. Bacterial A doesn't matter whether it's time point day 1 or day 5. Whereas for bacterial B, they're reacting differently to the time in terms of growth. And then here, it doesn't matter whether we have professionals or amateurs. While the professionals get better scores at whatever they're doing, the task B is still harder, equally harder for them compared to the amateurs. So there's no interaction. Interactions might be something that clicks for you when you're looking at your own data and your own study. The other thing to note from our two-way ANOVA is post hoc testing. Again, similar to the one-way ANOVA, if that p-value from the ANOVA is not significant, do not look at the post hoc testing. And also, post hoc testing is only done for the independents that have 3 or more levels, i.e. we had grass, tarmac and tracks, which is 3. We don't need to do it for independents that only have 2 levels. So our gender, male, female, there was no point in doing a post hoc there. And remember, you need to split that file to check for normality, but you've got to remember to remove that split file before you run the two-way ANOVA. I've made up my data, so it didn't violate any of the assumptions. But in reality, that assumption of normality quite often isn't met. And that's a bit of a problem. There's a few solutions. One is to try a transformation. Transformations, not everyone agrees with them, or not everyone thinks they're a good method. So you might have to look into your discipline to make a judgment on whether you want to do that. But there's a good resource here which explains what a transformation is and how to do a transformation. If you don't try a transformation, or if a transformation doesn't work, unfortunately there's no easy or reliable non-parametric equivalent to a two-way ANOVA in SPSS. So what I would ask you to do is just consider that a two-way ANOVA is robust to quite small violations. And so consider the type of skew that you have, and consider looking at the normality of your residuals, which we'll explain later. And also consider your sample size. If you have a very large sample size, it might not be appropriate or relevant to test for normality. Let's move on to repeated measures ANOVA now. There's some alternative names for repeated measures. Some people call them within subjects ANOVA, and sometimes literature calls it one-way repeated measures ANOVA. It's all the same thing. And what we're doing here is, these are for situations where you've got a study where you're measuring something multiple times. So it might be that you're measuring the same person 3 or more times, or an object, or you've got a sample and you're taking repeat measurements from that one sample. That's when you need a repeat measures ANOVA. So here, let's imagine that we've redesigned our stride experiment. We've redesigned it to take into consideration that some people have longer strides than others. So we're controlling for the individual. I want you to go to VLE and open up workshop data, stride, repeated ANOVA. This is where we redid the stride experiment, controlling for individual differences. So we're getting everyone to run on all 3 surfaces. So if we look at that data, it's here. You can see that it's set out quite differently now because we're following that SPSS rule where we have one person on a row. So we asked person number 1 to run on grass, and this is their stride length. Then the same person ran on tarmac, and the same person ran on track. And then everyone else did the same thing. Everyone ran on all 3 of our surfaces. In SPSS, we're going to check for normality, then we'll run a repeated measures ANOVA, and we're going to look at that output, including something called Mauchly's test of sphericity. And this terminology might sound intimidating because you've not heard it before. Really, it's very similar to what we've done before, so we'll explain that. So again, if we were going to run the test in SPSS, we could get a guide up. So I'm going to put in here, layered, repeated measures. Of course, you can use, you could use books for this. There's some good books out there that will give you instructions on it. And I'm going to click on one-way repeated measures ANOVA here. We've got an introduction to the test, and then we've got some assumptions. So I'm just going to point out 2 assumptions here. Assumption 2 is that your independent variable has at least 2 categories and they're related groups or matched pairs. So that means that if we go back to the data, this measurement is related to this measurement and they're both related to this measurement because they're all from the same person. And that's what's called related measures or repeated measures, matched data. And then the other assumption I'm going to talk about is down here, assumption 5, which is sphericity. And this might sound like a different word. It's actually just equal variances. But this time it's got a different name because we're looking at equal variances across repeated measures, which means the maths behind it is a bit different. So sphericity is essentially just the same as equal measures that we test for using a Levene's test. It's a very similar concept, think of it like that. So let's go to SPSS and we're going to check for the assumption of normality and we'll look for some outliers as well. So we'll go to Analyze, Descriptive Statistics and Explore as usual. This time what we're going to do though is we put all 3 of our columns in there because all of them contain the dependent variable. And we don't need to put a factor in here because it knows the grouping because we've got the group is in a different column. Go to my plots option and tick histogram and normality plots with test to get a Shapiro-Wilk. Click OK. And then you can see we'll scroll down and we've got 3 results here for Shapiro-Wilk and they're all above 0.05, so we've got normal distributed data. We can check that using the histograms and the QQ plots. Oh, and we've got a box plot as well, just to check for outliers. Tarmac histogram, tarmac QQ plot, a tarmac box plot to check for outliers. Track histogram, again, we might want to play around with the binning in that one. QQ plot looks okay though. And finally, the box plot to look for outliers. So now we're ready to run the test. So we can refer to layered to look at this. It will tell us to go to Analyze, General Linear Models, as we did before. But this time we're not going to click on Univariate. We're going to go to Repeated Measures. And this is where people get this pop up and go, oh, what does this mean? What it's asking you is to name what you want to call that repeated measures independent variable and then tell it what columns that measurement is in. It's easy for us because we've only got got 3 columns of data. But imagine when you have lots of data because you've got all these other variables of the person in that data set as well. So you can leave it as factor 1, but I prefer to actually give it the name of the independent variable to keep it clear in my head. So here, my independent variable is the surface. So I'm doing a test to check whether the surface has an effect on stride length. The number of levels are the number of groups in that independent variable. So I've got track, tarmac, grass, so I'm going to put a 3 in there. We've got to click add, so it accepts it. And then we're going to click define, and that's like saying, let's define which columns this independent variable is in. So here, it's waiting for you to say which of your columns these dependent variables are in, and which of the 3 independent variables. So click grass, tarmac, and track. You can see here it's named it within subjects. So we're comparing within subjects rather than between different people. We're comparing within a person. You can think of it like that. There's various options here. I'm going to click on the button options. And again, I like to get some descriptive statistics up. They can be helpful just to look at the means and standard deviations in numbers. I also want to click on estimates of effect size. That's going to give us a partial eta squared, which is useful to know how much of an effect the independent is having on the dependent. So we'll continue that. Then what I want to do is I want to compare among the different levels of my independent. So this is basically a post hoc test. I want to see where the differences lie between grass, tarmac and track. To do that, you click on EM means. You don't click on post hoc. Post hoc is for a between subjects independent, which will make more sense when we do a mixed model next. For something that's a repeat measure, we click on EM means. And we're going to say that we want to look at the differences for surface. And we need to tick this box to say that we're going to compare the main effects. And what I'm going to do here is choose this Bonferroni option. What that does is it corrects my p-values to make sure that they're accurate. So we're going to talk about type 1 and type 2 errors in a minute, at the end of this workshop, and that will become a bit more clear that if you do lots and lots of tests, you're more likely to make an error. Bonferroni corrects for that. Click OK. I also want to check for the assumption of sphericity. So again, this is like equal variance. But by default, that test is run. Click OK. And as always, I like to finish checking my assumptions before I look at the results of the test. So I'm going to check for sphericity by looking at Malchley's test results. So here it's down here. Malchley's test is sphericity. And you can see here that I've got a p-value. I want that to be over 0.05, just like in a Levine's test. So mine's is over 0.05, so I have this sort of equal variance among my 3 repeated measures. That's quite unusual though. Usually you get a significant value there, but that's not a huge problem. All you do is use a different result when it comes to actually looking at the main result of the test. So now if we look at the main result of the test, that's under this box here, test of within subjects effects. So what I'm going to do is look at this line which says sphericity assumed. If my Malchley's test had been significant, I would look at the greenhouse geyser line below. Because I've got sphericity assumed, I'll look at the top line. So I'm going to look at my p-value. So I can see that I do have a significant effect of surface. And then just like a one-way ANOVA and a two-way ANOVA, I'm going to report this F value and these 2 degrees of freedom, this degree of freedom here, and this error degree of freedom down here. So this 2 and this 22. I asked the test to calculate a partial eta squared. This is an effect size. So mine is 0.988, so partial eta squared is between 0 and 1. So you can see that my independent is having a really, really strong effect on my dependent. That's because I made up my data. So it explains how much of the variance in the dependent is explained by the independent. The other thing I'm going to look at, because I've got this significant p-value for my surface, is the post hoc test. So that's under pairwise comparisons here, this table here. So you can see here that surface 1, surface 2, unfortunately it's not used the codes, which is it makes it more difficult for me to interpret. So I have to remember which of my surfaces is coded up as 1, 2 and 3. So I can see that whichever is coded as 1 and 2, there's a significant difference. 1 and 3, significant difference. 2 and 3, significant difference. So all of my surfaces now, with that redesign in my experiment, I'm finding that there's differences between all 3 of my surfaces. Let's just go over our repeated measures ANOVA. We have to tell SPSS which columns contain the measurements of the within subject's independent variable. That throws some people, so just be careful what you're doing there. These are the options that I clicked on and what they generated. I clicked on options, descriptive statistics, just so that I get a mean, a standard deviation and a number. I didn't actually look at that output, but I would do in reality. I also under options clicked on estimates of effect size, and I clicked partial eta squared to get my effect size in that table. And then I wanted to compare the 3 levels of my surface independent variable. So I clicked on EM means, compare main effects, and I did a Bonferroni correction. So this is a post hoc test with correction. When it came to my output, I looked at Moxley's test for sphericity. Remember, sphericity is really similar to variance in a one-way ANOVA. And we want the p-value to be over 0.05, but it's not a problem if it's under. We then just use the result, which is Greenhouse Gesser result, and that corrects for the data not having sphericity. Our within subjects table in our output is where the result of the repeated measures ANOVA is, and we look at the p-value, the F statistic, the ANOVA degrees of freedom and the error degrees of freedom, and they're all under the within subjects table. So you want to report them. The partial eta squared is an effect size. Again, it's really good practice to report that, even though a lot of people don't. Let's say that our partial eta squared was 0.301. Then we can say that 30.1% of the variance in our dependent is explained by the independent. And you can think this is really similar to R squared in regression if you're familiar with that, if that helps. We also looked at the post hoc test, which was under the pairwise comparisons table, and we asked for these p-values to be Bonferroni corrected. Now, Bonferroni corrections change the p-value, or they adjust the alpha level, which the p-value's been compared to take into account that we've got an increased chance of making what we call a type 1 error, which we'll explain later. We've got an increased chance of making an error the more tests we do. I think this page here is the clearest piece of writing that I've found on what a Bonferroni correction is and what it does. So let's talk about a mixed ANOVA now. Mixed ANOVAs have a lot of different names. So some people will call them a two-way repeated measures ANOVA. Some people call it a mixed model, which is just the exact same as a mixed ANOVA. So we need some data. We're going to open Workshop Data Stride. It's the same experiment, same idea, but this time mixed ANOVA. And what we've got here is we've still got this within subjects independent, which is surface, because we've asked people to run, the same people to run on 3 different surfaces, grass, tarmac, track. But now what we've got is another independent, gender, which we can call a between subjects independent. That's because when it comes to gender, you're either assigned as male or female, and we're going to compare between different people, so between subjects. And the mix in this mixed ANOVA name of the test, it comes because we've got a mixture of independent types. So we've got a mix of within subjects independence and between subjects independence. Let's open up that data set. Here it is here. I've actually called it a mixed model ANOVA. And we can see now that we've got our within subjects, grass, tarmac, track. We've got our dependent values. And then we've got another column for our between subjects independent, which is gender. So we're going to mix these 2 independents into the same model. I'll run the model in SPSS and then we'll go back to the slides and recap. As always, we can, whatever resource you use, you can look up a guide for this. I'm going to type in mixed model. It's come up as mixed model ANOVA. And again, it talks quite a lot about the test because it's a bit more complicated test when you're mixing within and between subjects. It can also be quite difficult to identify when you need a mixed model. And we've got assumptions which are really similar to before. We've got this assumption of normality, just in the same way that we split our file in a two-way ANOVA, we're going to have to split our file for a mixed model in order to test for normality. So let's demonstrate doing that in SPSS. We'd go to Data, Split File. I'm going to compare groups and split the file by gender. Again, nothing happens. We just get this little message which says that the file was split, but our actual data set doesn't look the same. Then we're going to go to Analyze, Descriptive Statistics, and Explore. We're not going to put our gender in because it already knows that we split, the data set's already split by gender. We're just going to put in our other independent. And then we can see that what it's done, or should have done, try that again, because what I forgot to do is click on plots and tick histogram and normality plots for test. Try again. Right, that looks better. We've got some Shapiro-Wilk results this time. And we can see now that female grass, we've got a result, female tarmac, got a result, female track, we've got a result, and the same for male. And we've got all our various histograms and our QQ plots as well. Now what we need to remember to do before we run the mixed model ANOVA is take that split off, because that will not run the mixed model correctly if we still have the split on. So go to Data, Split File, and choose Analyze All Cases, Do Not Create Groups, and OK. So now we're going to run the mixed model. It's the same options we go to as when we ran the repeated measures. Because it is effectively a repeated measures, we're just adding in the between subjects independent. We're just adding in gender as another independent. So again, we come across this pop-up. I'm going to put in what my within subjects factor is, which is surface, my within subjects independent. I've got 3 levels, grass, tarmac, track. Add that, define it. Hopefully you're getting more familiar with this process now. This is the second time you've seen it. Tell SPSS which columns the data's in. And now it's got a box here for our between subjects factor. So we're going to put in our between subjects independent gender into that box. There's a few options that we can choose. So I would click plots because I want to create a plot for the 2 independent variables so that I can see the interaction. So I'll put surface on horizontal line, and I want gender as separate lines. Add that. Again, if you're more comfortable with bar charts, you could use ask it to create a bar chart instead of a line chart, line graph. I don't need to click this post hoc test here because I've only got 2 levels of my gender. So if there's a significant p-value, I know the differences between male and female. I do want to click the option which is EM means because I want to see where that difference is for surface, if there is a difference. So again, I'm going to put surface here, tick compare main effects, and choose Bonferroni. What else do I want to do? I might want to click options. Again, I like my descriptive statistics, I find them useful. And again, I'm going to click estimates of effect size because that's going to give me partial eta squared. So it'll tell me how much an effect my independent is having. Also under options, we have homogeneity tests. We can tick that to test for equal variance. By default, a test for sphericity. So that's the equivalent equal variance, but for repeated measures. You can think of it like that. And click OK. So I've got some descriptive stats there. I'm going to finish checking my assumptions by looking at this Moxley test for sphericity. You can see here that I've actually got a significant result here. So I would use the greenhouse guesser results when it comes to interpreting the results. I also want to look at my Levine's test. Just find it. Here we go. Levine's test for equality of error variances. So then I'm going to use based on the mean, and I can see that for comparing the genders in grass, they're equal. Comparing the genders in tarmac, they're equal. Comparing the genders for track, they're equal. So then I want to look at the actual results of the test. Oh, I've gone too far. trying to find it. Okay, so here we've got the result, which is for the within subjects effect. So the within subjects independent variable is our surface. So here, surface, I'm going to use greenhouse guesser, and I can see that I've got a significant effect of my surface. So surface does affect the stride length. I would also report my F value here, and then I've got degrees of freedom here. I've also got an error degrees of freedom down here. And then it gives me an interaction between surface and gender. But what it's saying this time, if I look at this p-value here, 0.718, that there's no interactive effect. So that's me got the p-value for the surface. Now what I need to find is a box which says something like between subjects effects. Here we go. And that's going to hold the results for my between subject independent, which is my gender. So here in this line here, gender is also having a significant effect. So we've got a significant p-value here. Again, I'd report my F value and my degrees of freedom here and here. This 1 and this 22 would go into my report. We have a pairwise comparison box again. So I want to know which surfaces are different from which. And again, we can see we've got all significant p-values here. So track, tarmac and grass are all different from each other. Let's go back to the slides to recap our mixed model then. So remember, it's running the same way as a repeated measures ANOVA, i.e. it's under the same menus, except that we add an extra variable under that between subjects factor, so we added gender. The options are really similar to the repeated measures ANOVA. We're ticking descriptive statistics under the options button and estimates of effect size partial x squared. We didn't actually look at that. And then we clicked EM means, compare main effects and Bonferroni, to get a post hoc for our surface. We did click plots as well to enter our two independents, and that created a plot. Actually, I will just go back to the results and show you that. Where's my output window? Here we go. Oh, here it is. I missed it. So you can see now that there's certainly a difference in the genders. So females are in the blue, and they've got lower stride lengths, shorter stride lengths than the males, which you might expect. But this time the lines are really parallel. So that means that there's no interaction going on between gender and surface. There's just differences in the three types of surface, 1, 2 and 3. For the output, it's the same as repeated measures. We're looking at the Morsley's test to make sure that we've got sphericity, to make sure that assumption's met. Then we're looking at the F, the degrees of freedom, and the p-values for the within subjects independent. And we're looking at pairwise comparison post hoc test to see where those differences lie. Plus, because we've got this between subjects gender, we looked at the F degrees of freedom and the p-value for that as well, and we looked at that plot to look at that interaction between the two. Points to note, there's no post hoc for between subjects in our case because we've only got 2 levels of gender, but there might be if you were running your own mixed model. And also, we can add more within and between subjects independent variables to the test. You can a mixed model can get quite complicated if you like, but you can test the effect of lots of different independents. This last bit talks about some statistical concepts that you might find useful to understand. Let's start with alpha levels, which are the same as significance levels. We're talking about 0.05, 0.01 and 0.001. So you might be familiar with those numbers if you've been reading papers, journal articles. What we need to do is choose an alpha level before we run any test. So when I was running those tests, I had it in my head that I had chosen an alpha level of 0.05. I was working with that alpha level. There's 3 common alpha levels that we use, which we can compare our p-values to: 0.05, 0.01, and 0.001. And these are just standard significance levels that you find. Depending on your discipline, will depend on which one you use. The idea is that the lower the alpha level, the less willing you are to reject that null hypothesis. So you can imagine that if you're working with 0.001, let's say you're doing medical trials, quite often they work with 0.01, and you've got a null hypothesis that, let's see, a drug doesn't work or something, then you're really, really not willing to reject that null hypothesis. You want to be sure that a drug you're going to give to someone actually is going to work and have an effect. So we can say that a lower alpha is going to reduce the chance of what's called a type 1 error. So that leads us nicely on to what is a type 1 error. This is when you reject that null hypothesis. So you reject that there's nothing going on, there is something exciting going on, we have a difference, or there is an association, but actually in reality that null hypothesis is true. So the example I could use to demonstrate this is the Andrew Wakefield case, an MMR vaccine. If you want to read more on that case, there's a link there if you're not familiar with it. It was widely reported in the news at the time. What he did is he claimed his data rejected the null hypothesis that there was no association between autism and the MMR vaccine. So he had this null hypothesis that there was nothing going on between people who had autism and people who'd had the MMR vaccine. He'd done a study, and then he rejected that null hypothesis to say that there was an association. The problem with that is that as more people did research, we realised that that null hypothesis is actually true. There is no link between autism and MMR vaccine. We're quite certain of that now, given what's happened following that, people checking his results. So what we can say is that he made a type 1 error because he rejected a null hypothesis that was true. So that's a case of a type 1 error. I suppose you can think of type 2 errors as kind of opposite to that. A type 2 error is when you accept a null hypothesis when it's not actually true. So you accept a null hypothesis when you really shouldn't have. So I'm going to use another example. Let's say that we've got this null hypothesis, which is that there's no difference in height between men and women, right? We're working with that null hypothesis. And let's just say we measure the heights of men and women, then we run a test, and we get a p-value of 0.13. So whatever significance level, alpha level we compare that to, it would be considered a non-significant result. We would conclude that there's no difference in height between men and women, and therefore we would be correct in accepting our null hypothesis given our test results. But this would be wrong, because the truth is, reality is, that men and women are different heights. There's a lot of evidence for that, we know. So what we would have done in our study is have committed a type 2 error. That's where we accept a null hypothesis when the reality is that it's not true. So errors connected to something called power. People talk about the power of a statistical test, and this is what they're talking about. The power of a test is the likelihood that it's going to detect an effect if one exists. So it's going to detect that the independent variable is having an effect on your dependent variable. Tests that have more power are good because they're less likely to lead to an error. They're less likely to lead to a type 2 error. When assumptions are met, so when we've got this data and we've checked it for assumptions and that's all okay, a parametric test is going to have more power than a non-parametric test. So it's going to be more likely to find this difference or this association if one exists. However, if our assumptions aren't met, then we could maybe make an error. So that's why it's just important that we're happy the assumptions are met. Because parametric tests are more powerful than non-parametric tests, then we want to preferentially use a parametric test over a non-parametric test. So we always want to try and use, let's say, an independent two-sample t-test rather than a Mann-Whitney U, because it has more power. The two-sample t-test has more power. So power is affected by a few things. Sample size is one of the things that will affect the power of your test. The bigger the sample, the easier it is for a test to come up with the right answer. And to demonstrate that, think about this. The power of a test would be quite low if we only measured the heights of 3 men and 3 women. So if we did that, we've only got n equals 3 or n equals 6, depending on how you look at it, and we put that into a statistical test, and there's not a lot of information for the test to go on. So that test would have really low power. Compare that to if we measured 100 men and 100 women, then our power has got much more test. It's much more likely to come up with the correct answer. The other thing that's going to affect the power of our test is effect size. So if there's a really, really big effect, then the test is more likely to find that effect. You can say that the test has more power because the effect size is large. It's got more chance of detecting the effect. So again, let's think about our height example. Let's just say that in reality, there's a really large effect of gender on height. So that means that, let's say there's a huge difference between men and women. Men are 50 centimetres taller than women. That's going to make it really easy for a test to find a significant difference. But the reality actually is a little bit different. The difference between men and women, at least in the UK, is more like 13 centimetres. And that's not as big an effect of gender on height. That means that the test is less likely to find a difference. So effect size determines the power of the test. You don't always know the effect size in a situation, but we can calculate a rough effect size given some data. So we can assign a number, so we can quantify effect size. And it's good to report effect size because it communicates to a reader how much of an effect the independent has on the dependent. There's a few common measures of effect size. So you might or might not have heard of Cohen's d, which might be used after you've ran a two-sample independent t-test. We've looked at partial eta squared in this workshop. That's an effect size. Other effect size you might be familiar with are the correlation coefficient r when you run a correlation, or r squared when you run a regression. They're all effect sizes. These are the references that I've used, and that's the end of the workshop.